Let's consider a situation where you have a turkey. In one case, we'll just put it in an oven, and in the other case, we'll put it in a turkey fryer. Now, if you go to Wikipedia or some other books or information, you'll find out that a 15-pound turkey will take about 1 hour at the grease temperature of 350 degrees. And if you look at putting it in an oven, they'll tell you that a 15-pound turkey will take about 5.5 hours at about 350. So let's take a look at this and think about this for a minute. If we wanted to model the turkey as a sphere, you're putting it in a substance in which the same turkey takes a different amount of time based upon what you're putting it in. So the conclusion would be is what you're putting it in is the determining factor, and that is either air or oil. Now, if you look at the equations, you'll find out where this differing time requirement comes to play. And it's often called lumped heat capacitance system, and the equations have to do with HA, the temperature minus T infinity, which in both of these cases 350 degrees, and that heat is balanced by, okay, so here you have a turkey, you have this amount that's basically dissipated. Now the assumption is going to be made that the outer skin of the turkey is an average, and that the coefficient, the heat transfer coefficient, is going to be the average around the entire turkey. If you set that equal to, you will get heat loss through there, rho C, a volume, and a change in the temperature with respect to time. Now we're going to talk and look at some of these terms, but the actual solution becomes T is equal to T infinity plus T naught minus infinity times E to the minus HA over rho C volume times time, and you can put a bracket around this. Now let's consider the case in which the turkey was put in the oil. If you were to put a coordinate R and it was a perfect sphere, and you dump this in, say this is the external wall of the turkey, so this is the external wall of the turkey. When you had the turkey at time t0, temperature at t equals 0 is equal to t0. Now you threw the turkey in the fryer, and let me do the plot a little bit differently. So here is 350, and here is the, say you put it in and say the turkey was at 50 degrees. So at t is equal to 0, this is the temperature distribution as a function of R. Now immediately In the oil, there's going to be so much heat that transfers out that this temperature is going to pretty much go like this. So the temperature inside the turkey as a function of T and R so if this is classified as the temperature in this region, it's not going to be constant because it took so much heat out so quick that the outside skin may burn before the temperature inside the turkey gets hot. And let's look at how this all relates to what is commonly called the Biot number, which is HS over K. And let's look at each of these terms. Now, S is going to be a characteristic length, and usually we consider that characteristic length to be the volume over the surface area. So if we consider this to be a sphere, what we end up with is 4/3 pi r to the third over the surface area is 4 pi r squared. So what we end up with is this and this taking out one of those, this taking out that, whoops, it ends up being r over 3. Now the K, let's look at our K. Now what I'll do is make a rough estimate of the conductivity of oil and the conductivity of air, roughly. So of oil, this is not accurate, you might want to get a better value than this, but I got about 0.14 watt meter degree K. For air, roughly 0.0, say 3 watt meter degree K. Now the H value. The H value is a value that we're going to just simply approximate to get a value out of it. If in fact the resistance to heat transfer in the solid is large compared to the resistance. Well, let me rephrase that. Okay. In the lump capacitance system, we're assuming that the temperature is uniform in the solid body. Okay, if the assumption is equivalent to saying that the the surface basic convective resistance is large compared to the internal conductance resistance. If this is the case, then the assumption of a uniform temperature is okay. What this means, okay, is that the Biot number is less than around 0.1. Now let's take a look at our turkey and say pretty much that our turkey has a radius of, say, 1/6 of a meter. The way I got that is started thinking that maybe it was about 6 inches are roughly 6 inches, which would be a radius of a foot. A diameter of a foot. So this would be 12. You stack that up and you end up with 1/6 of a meter is about 6 inches roughly. So if we just guessed that, say it was that H was watts meters squared degrees C or K, then a Biot number for the oil would be HS over K, or say 10. S is now 1/6 times 3, and the K would be either 0.01 or 0.03. So let's do this one, and we'll call this air. I would get around 18 and change. If in fact though it was for turkey 0.14, I would get about 4. Now neither one of these are less than 0.1. However, let's make one equal to 0.1 by changing this, the unknown here. Since I guessed this, let's change this number and this number in such a way that one of these two is 0.1. Okay, so the way I will do this is I'm going to do it this particular way. I'm going to look at this particular case and I'm going to say, what would H have to be for this to be 0.1? And if I did it correctly, I would have gotten a value of 0.054. So for air, if I had, let's just say that in both cases I had 0.054, then the Biot number for air would be somewhere in the range of 0.1, and I'll just say it like that. The Biot number for oil would be 0.054, 1/6, 3, and divided by 0.41, which would give me a Biot number of 0.0214. So doing this in oil versus air, if the coefficient was slightly higher, or say instead of 0.05 it say was 0.1, the assumption in air would probably not work okay. However, in our case, in our lab, what we're going to operate on is we're going to operate under a global thing. We're going to assume that we are okay, that the Biot number is less than 0.1. If that's the case, then this equation up here becomes valid. And we're going to purely operate over that for right now. And what we're going to do is I'm going to copy it and run all the way down to here, say, and paste it. I'm going to take a look that this is the assumption we're going to use. The data I received in lab I don't have right now. So what I'm going to do is I'm going to just do this with a set of false data and say, here's what we're going to do. It doesn't matter whether you heat a turkey up or you cool it down. We're going to take our cold sphere, and we're going to say our T naught, we're just going to guess something was 70 degrees, and then our T infinity was, say, 180, and we took our sphere and put it in there. If that's the case, let's take a look at several values of this and look at MATLAB and see what we can come up with here. Okay, let's assume that we took our 70-degree sphere and put it in a liquid vat of 180-degree water, and our solution should look something like this. This equation will predict all of the different various circumstances. Even if we took a warmer sphere, dropped it into a colder liquid. This equation takes care of all of them. It can be written in a more concise fashion like this. Rho C and V, and this may lead us to a transformation. But before we get there, let's take a particular data set as a case in point. What I'm about to do is move a series over in front of the recording, and let me manipulate things around. Now, since I'm doing this, I am going to do MATLAB. If you want to do something else, have at it. So let's run this. Take a look at it, and this is the what I have. Now all right, so what we have here is we have a dot for each one of the data points here. So your temperature comes across this way, and it goes throughout time, and you'll notice time goes from 0, 5, 10, so it's every essentially 5 seconds. This is where the raw data would come into play here on your case. So let's take a look at how we might fit this or determine information from this. First thing we need to do is we need to determine all the values that we have right here, with one exception. Let's take a look at it. Let's move down, and we don't know this. This can be backed out and pushed in to figure out the Biot number. But first, let's take a look at this. Okay, so what would be A, V, rho, and C? And that's for you to determine for each of your cases. But I'm going to come up with some mock data, and we're going to use it particularly right now. And from that, you're going to have to come up with the correct information. So for the time being, ever so how inaccurate this may be, I've decided that these are the values I'm going to use. Now, what you're going to have to do is you're going to have to realize that for a sphere, this might be, and you better go check this, is 4 pi r squared. This might be 4 over 3 pi r to the third, but that's something you better check. I'm not going to claim that what I just said was correct, so as a result I'm just going to scratch it out and let you go figure out the rest. But this is going to be the density, and this is going to be the C sub b. You better figure out the correct units on all these. The question is the data we have consistent with the fact that the Biot number is less than or equal to 0.1? Now, of all of the values that sit up here in this equation on the top and bottom, I know everything with the exception of h. And I also know that if I'm paying particularly close attention, the Biot number, can't seem to get rid of that value, but that's okay, is equal to h s over k that we had up here. h s over k, where s was nothing more than this. So our key is if somebody can tell me the conductivity of the object we put in there, the S and then the H, does it satisfy this? And let's check this out. Let's bring back our equation and let's take a look at something here. Okay, if we do our plot one more time and we take a look at it, we get our equation that looks like this. I mean, our plot that looks just like this. But let's do something interesting. I know that the T naught and the T infinity, so I know that T infinity here was 180 because I took the temperature of it. I knew that T naught was equal to 70. And so what I did is I'm going to set up a term theta equal to, and what I'm going to set it up equal to is this. If I look back over here, we'll leave that there for the moment, come back over here, and this is what our theta is going to be equal to: T minus T infinity over T naught minus T infinity. Let's take a look at what that equation might look like. Okay, so let's just hang on, let me get it. Okay, let me bring it back over here. So that's what I just typed. And here's the next thing I'm going to do. I'm going to plot that as time versus theta. Now, bring the plot back and notice something interesting here. Now, before I do this, I should fix this plot because it shouldn't be looking like that quite yet. So there's my data points. However, let's take another look here. An interesting thing occurs here, and it occurs in this particular way. If I were now to look at theta as a function of, theta now as a function of time, it would simply look like that, where k was equal to HA over rho C V. Now if I take a look at this, Yes, in fact, I always get a plot that looks like this. The rate depends on K. If K moves in a particular direction, it will damp out much quicker. It could go out further and further. Now, I want to determine K here. The best way to do it with a set of data is a transformation. The transformation can be seen logically if we go back to MATLAB and take a look at something. I added a line here, and I should put the data like that on it. Let's run this and see what you get. Whoops. You get something like this. Now there is some jumbling in the data, but what you have to remember is that as you move further and further down this line, there might be some difficulty in the fitting here, but we'll address that later. It looks like a straight line. Why does it look like a straight line? Because what we're doing is we're plotting y as a log. So how do we fit that in MATLAB? Let's take a look. We might get some insight here by taking the natural log of both sides. If we did that, and you can try this on your calculator if you felt like it, or if you just felt like, here, let's type in that log of any number. So if you put any number you want in there, you're going to get the number back. So this implies that this is equal to nothing more KT. Or you could call this a new function instead of theta. I don't know, call it gamma as t. Now there's something fairly interesting here. The plot we saw looked like this, and it looked like it gumbled up down here, but let's look at what we have when we're back along in here. Now we had our first data point here at 5 seconds, but we had one at 0. What happened to it? So in essence, if we look at the data, we started with a data point at time equals 0 of 70 degrees. Where did it go? And let's take a close look at it and say, when time equals to 0, then t0, in other words, theta at time equals 0 is equal to t0, t infinity, t0 minus t infinity, or it's equal to 1. Okay, so let's grab that, move it down here, and let's think about this for a second. If that were the case, we would be taking the log of 1 here. Let's do so. Find out what we get. Type it in your calculator and you'll get 0. So this means regardless of how you start this condition, you have an equation in which the intercept sits right here. So usually you have a t plus b, where b is the intercept. But in this particular case, t is equal to 0. The log of that gets you back there. Let's see what I mean by that. Some insight can be gained by looking at the plot again, pressing the hand and pulling it down. What you notice is the appearance of that dot right there, or of the O, the initial time. So our biggest problem here is how to find this particular value, the k. Now, here's what a proposal might be. To go ahead and find theta, okay, and we do so. We find our theta right here and look at it as a function of time. But transform it. What I mean by transforming it, let's take a look. We're going to put a breakpoint right here. We're going to run it down here, and I'm going to hover over theta. What you're going to find is a series of values here starting at 1 and ending very, very close to 0, but not quite making it to 0. So if I had this set of data, how can I determine what the k value is? The k value being this value right here. So what I'm going to do is I'm going to take the log of my data set. Now see, I don't have a data set over here, but I do have a theta here. And I end up with a kt over here. So here's what I'm going to do. I'm going to come back to my MATLAB. And this might be a plot, that's fine. But then I'm going to take the log, I'm going to do log of theta is equal to, and I'm going to look at those values. So I'm going to do a save, and I'm going to rerun the code, but this time I'm going to do one step. I'll hit the F10 key, goes one step, and I can look at the data. It goes from 0 down to a -7 or so. Okay, your first glance is now I've got a series of data. I can actually plot these as a function of time. If you want to see it, plot the log of theta as a function of time, and I want them to be a series of O's. I'll select this and hit the, well, let me just do it this way. I will save it. I'll run it again, hit the F10, undefined log theta, I forgot to put the, save it, run it again. I'll do one single step, and I believe I end up with something along, wait a minute, that's not it. Because let me try that again. I will run it. Here's what I'm going to do. Just put a pause there so I can breakpoint that, save it, and then I'm going to run it again. At first glance, I thought I made a mistake, but I did something foolish. I should have put the time here. Now let's try it. Okay, so that looks like the plot. This is the power of the value all the way down. So let's compare two plots here. What I'm going to compare is figure 2 to figure 3. Let's bring figure 3 in here and look at it right here, and let's bring figure 2 and look at it right there. Now, pay really close attention to something here, because what we're doing is this. Let's look at the exponent, not the value of 10 here, but the exponent. So let's go and scratch these out and look at this. Okay, your last. Okay, this might not be perfect because actually I believe I took a natural log instead of a base 10 log, or vice versa, but we can fix that. But the plot looks exactly the same with one exception. That's going to the -7 down here when this is going to the -3. So I may have to fix my logs from natural logs to base 10 logs here. But I can fix that here in a second. The key is I can take this and run it in a manner that I can find that slope. Let me try to fix those base 10 logs and natural logs here. Let's run this thing one more time. And what you get is a little bit better, because now let's look at it. Okay, I changed it to base 10, and what you see is this one ending up about right there, and this one ending up about right there. So in fact, this is the exponent that's sitting right here. So 1, 2, 3, 4, 5, the sixth one. 1, 2, 3, 4, 5, and the sixth one here. So if I went across this, I would see this. Now, that represents a problem. What does the problem represent? Well, here, let me fix it. So essentially what I need to do is take this slope. Now this slope will not be a direct correlation of the k, but it might be close with a transformation. Now the question is what do I mean transformation? Let's take a look at our equation. Our equation looks like this. Let's do e to minus kt. Now, what I'm proposing is to take the log base 10 of both sides. And then what I'll get is some sort of factor minus, say, k t, where the k is not the kappa there. But the thing is it would still be log of base 10 e to the minus kt. This is what I'm searching for. This is what I'm going to find. So I'm going to have some new function, say gamma of t, in which I'm going to scratch, then I'm going to take a natural log, because it really doesn't matter. I take the log base 10 of 1, I still get 0. But I'm going to come back and pay close attention to this. Let's find what k is. Now realize we just have a simple set of data over here. Okay, we're going to go in here and look for polyval and polyfit. Okay, P-O-L-Y-F-I-T. And here is our polyfit. Okay, or we can do it right here. Here. Here's our polyfit. We're just going to fit coefficients to a polynomial, a degree n that best fits this. So x and y, and we just want a linear. So here's how we're going to do it. P, well, let's make it capital P, is equal to poly fit of what? What is the x? The x is the time. The y is going to be my log base 10 of theta. And I just want a basic linear fit. So I get P equaling to this. Now let's take a look at how this thing fit what we're trying to do. By looking at polyval. Okay, y, for example, is going to equal to polyval, of my p and my time. And this time I'm going to do a hold on, and I'm going to do a plot of time y. So let's take let's save this and let's step through here. I'm going to use the step key. Okay, let's take a look at, this is figure 3. I'm going to go ahead and drop it in here so I can look at it while I'm executing these statements. Okay, so I can hit one step and I get my values. Another step, and then I plot those on there. And what you see is a curve that goes through here, or I'm sorry, a straight line. Looks like it fit the plot fairly well. So with that, what's the information I need out of here? Let me go back. I've got two values here. You have to look really close as far as the one you're mostly interested in. And it's actually pretty easy if you look at this. So from polyfit, you're fitting this. So this means your values of P1 would be associated with x, and this would be the nth power, so that would be to the first power, plus Pn plus 1, which would be 2. This one is going to be, the second number is going to be the intercept, which should actually be 0, because you can see it's pretty close to 0. This is the number that is the slope. So the first number is the slope. Let's take a look at it. Pull it back out. Okay, so my first number back there is 0.03. So this means that I get minus 0.03. T is equal to log base 10 of e to the minus kt. All I have to do is stick in just 1 second, and then I can do 10 to the minus 0.03. So if I do that, then I get is equal to e to the minus k. And then what I can do is take the natural log of this. That will give me a number. And let me find that out. However, I could actually automate that in MATLAB. Let's see if I can find MATLAB window again and do something like this. Okay, so I'm going to have a series of P here, so I'm going to take I got to look back at the equation. Let's see. I'm going to take or find the log of 10 brought up to the power of P, the first entry. Call that my K equal to. So here's what I'm doing. If you look at this statement right here, it should mimic this, except now it crunched it way down. But that statement, log of 10 to the 3, okay, so that will give me my K value. So now if I save this and rerun it to stop it right up to here, my K value is minus 0.0691. Now what do I do with that? Well, I don't know. Hang on just a minute. K would be equal to minus 0.0691. So that's my K that showed up back here, or right there, or right here. So let's take a look at this, okay? Lasso this thing, and I have no idea why I'm carrying more than that. Okay, here we go. Run it down the page until we're about right here. Now, what we want now, we have to remember, we wanted H out of this. So this means that if you look back, and I have not put any of this in my code yet, but let's go back and take my values and put in there. Now before I go on any further, let me fix something here in a symbolic method here. Here's what I'm going to fix. This was not the conductivity, but just a time constant. So don't get this term confused with the conductivity. It is not the conductivity. And this one will make different than that one because it is. It has to do with the fact that you're doing a base 10 log of that. And now we're back to this. Our whole goal is to find H was equal to our time constant, rho C volume over A. Let's check this out, because actually the data that I generated as a false experiment, because at this particular point I don't have the right, I don't remember the data. Okay, now there's one other thing I should add here, and looking at real close at this equation, because if I extract this down, I'm going to get minus kappa is equal to logarithm of base 10.03, or I could put a minus here. Okay, so I need to fix that over here on my MATLAB code. Now, luckily, it worked out perfectly. It wasn't luck, I guess. It was just an annoyance, but in fact, this is the final equation right here. Let me take you through what happened here. We're going to save it and run it up to this point. At this particular point, we're about to polyfit this plot. Now this plot is figure 3, and it sits over here. Now we got too much information here. Let's get rid of all these plots, and then I'll rerun this thing again. There's too much going on here. Get rid of all my plots, rerun the thing. Alright, here's my plot. I'm going to attempt to fit this, 10, I do so. Then I figure out my K, which is 0.0691. These are my values that I looked up, but you need to double check these. These are for brass. Okay, now this is the value that comes out, and this K actually came from here, and I get an H of 1.91. Now in fact the data was generated from 2. H is equal to 2, so that's pretty reasonable. You plot it, you go back and look at figure 3, and I'm sorry, it's not plot yet. Hold on, now you plot it. And this is the curve that fits it. So it fits it fairly reasonably. Now, this is something you need to be considerate of. This is data that was generated, and you can see the uncertainty already here. So this is a very sensitive experiment, and we might come back and deal with that in our uncertainties after we deal with this turning in this lab. So at this particular point, I have my H value. My H value ends up being equaling to 2. Now, did we satisfy things? HS over K. So our Biot number is equal to HS over K. H was 2. S, in this particular case, we'll figure out from the volume divided by area, and then the K is the K for brass. Let's go take a look at our MATLAB code here. Okay, let's make our last thing calculate the Biot number. Now, Biot number is going to be equal to H times volume divided by area divided by the K of our brass. So with that in mind, let's run it all the way through. Okay, I have a breakpoint that happened right there, and I go on down, and I got a Biot number of 1.4 e to the minus 4. That's easily under the consideration of being less than 0.1, so we're fine there. So with that, that's the entire piece of information of how you get through this and how you calculate your H value experimentally. I'll add more to it later, but any way you do it with the data going up or down, it'll still come up with the same value.